Algebra 2, Chapter 11, Section 4, Natural Logarithms and Other Bases. So up to this point, we've just been talking about a logarithm in terms of base 10. So we were talking about how a log of a number tells us the power we must raise 10 to get that same number. In other words, log of x equals y is equivalent to x is 10 to the y. Now we'll talk about logarithms of other bases. So logarithm base b of x is y if and only if x is b to the y. So now instead of 10, we just have b. And we write the number b here. So this could be log base 2 of x is y if and only if x is 2 to the y power, or any other number. And that's indicated in this subscript beside the logarithm. When the base is e, which is the number that we talked about a few weeks ago, e is known as the base of the natural logarithm. It comes up whenever you have continuous growth, and also comes up in other places. When the base is e, the base of the natural logarithm, we write ln for log instead. So ln means log base e. Okay, we write ln because that natural logarithm comes up all the time in math, so we want a nice, short, easy way of writing it. So ln for natural log of x is y if and only if x is e to the y. Remember, e was 2.71 and so on. It's a number. Logarithms of a particular base undo exponentials that use that base. So for instance, the log base 2 of 2 to the n is n. And 2 to the log base 2 of n is n if n is positive. The natural log of e to the n is n, and then e to the natural log of n is n if n is positive. These are all true. What's not true is if I take the natural log of 10 to a number, I don't get back just that number. I get back, this number could come in front, and I would get back the natural logarithm, which is e based. What is 10? If I take, what power do I have to raise e to get 10? Times this input. So you only undoes the the logarithm of a particular base only undoes exponentials of that exact base. But you can use any logarithm to do log of both sides and get the right answer. So let's go back, use the definition of logarithm, and find these values. So log base 2 of 64 is asking what power do I raise 2 to? What do I have to put here? What power do I raise 2 to get 64? That's what this is asking. So 2 to what power is 64? Well, if we think about 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32, 2 to the 6th is 64. So the answer is 6 to part A. B, what's the log base 3 of 27? What power do I raise 3 to get 27? Well, 27 is 3 times 3 is 9 times 3 is 27 is 3 cubed. So the answer is 3. What power do I have to raise 5 to get 625? Well, 625 is the same as 5 times 5, which is 25 times 5. It's 125 times 5 is 625, which is 5 to the 4th. So the answer is 4. We have to raise 5 to the 4th power to get 625. Calculators have a button for both natural logarithm and the base 10 logarithm, log. However, they do not have a general button for log base b. So how can we use a calculator to find the log base 2 of 1024? Well, we don't have a button for it. So if we think of the definition of logarithm, the log base 2 of 1024, what we want to know is what's the output? What does it equal? If we rewrite this using the definition of logarithm, we could write 1024 is 2 to the what power? If we take the either logarithm, we could do natural logarithm or the base 10 logarithm of both sides, we can solve this exponential equation. We have log of 1024 is log of 2 to the x. Pulling the x in front, we have log of 1024 is x log 2. Dividing both sides by log 2 and flipping the equation, we get x is log 1024 over log 2. Okay, so we can use a calculator now to find the answer. So pull up calculator and find log 1024 over log 2. And we find the answer is 10. That makes sense. 2 times itself 10 times does equal 1024. And the logic that we used to find this calculator solution was, we have a log base b of x. We said, okay, we'll set that to some unknown y. Use the definition of log base b to write an exponential equation. X is b to the y. Take log of both sides, and note here this could have been natural log of both sides. Pull the y in front, divide by log base b, and we get that the output of log base b of x has to be log of x over log of b. So we can write this general equivalency. Log base b of x is equivalent to taking the logarithm of x base 10 and dividing by the logarithm base 10 of b. And since we could take the natural log of both sides, you could also define this as being the logarithm base b of x is the natural log of x over the natural log of b, or any other base logarithm. And this is why your calculator doesn't have a log base b button, is this rule is pretty easy to remember. To find the logarithm of a number to a particular base, take the log of that number, divide by the log of the base. And that's how you find it. So now, use a calculator to find log base 2 of 1,000. And this one's not going to be a nice round number, so it's not a power of 2. So we have log of 1,000 over log of 2. 9.966. 9.966 is A. Log base 3 of 50. So take log of 50, divide by log of 3, and we get 3.561. As the answer to part B. Part C, what's the log base 5 of 500? So log of 500 over log of 5, 3.861. So we have to raise 5 to around the 3.861 power to get 500. The value of an investment in year T is given by V is 1,000 times 1.082 to the T. Give the initial value, the annual growth factor, percent growth rate, and the continuous growth rate. The initial value, A, is 1,000. The annual growth factor, B, is 1.082. The percent growth rate, R, we subtract 1 and make it a percent, 8.2%. But the continuous growth rate, K, we have to think back and remember, continuous growth was modeled by A, e to the kt. And K is the continuous growth rate. So we know A to the bt has to equal this A to the ekt. So writing e to the akt on the other side of the equation, we can figure out how to convert the growth factor into the continuous growth rate, because here we can cancel A, and T, B to the T is e to the kt. If we take the logarithm of both sides, here we have T log B is kt log E. And we can do this with base 10 logarithms, but it might make more sense to use the natural logarithm. The natural logarithm of E is just 1, or remember the natural logarithm undoes e to the kt, so we can get rid of that. And we just have T times natural log of B is kt, Well, the t is on both sides and it'll cancel, it's non-zero. That gives us that k is the natural log of b. Another way of thinking of this, using the definition of natural logarithm, is that e to the k is b. Okay? You can kind of see that just by looking at this equation. So we can find, now that we know how to use a natural logarithm, we can find the natural logarithm of b. B was 1.082, and get the continuous growth rate. So that's a lot simpler than any kind of guessing and checking of any sort. So the natural logarithm of 1.082 is 0.0788. And as a percent, that's 7.88%. That's our answer. Now let's apply log base 2 to music and do some examples here of an application of a logarithm that's not base 10 or base e to a real world problem. So in music, the pitch of a note depends on its frequency. So a note that sounds higher vibrates much more quickly than a note that sounds lower. The A above middle C on a keyboard, so if we think of a keyboard that you might have on a piano, if we have, would be a C here, and if this was the middle C on the keyboard, then this would be an A. And then if this was the middle C, this would be the A above middle C, which is known as A4, because this is known as C4, the middle C. The A above middle C in standard pitch is tuned to 440 hertz. Where hertz, if you don't know, hertz is the number of times something vibrates in a second, so it's the same as 1/seconds. Each time you go up an octave, so if we went up to the next C above C4 from middle C, the frequency of whatever that is doubles. So the A above this on the keyboard, imagine a piano, A5, the A above the middle, the A above middle C is double, 880 hertz. And each octave you go down halves the number of hertz. So the frequency is half as you go down an octave. Okay? So the number of octaves between a note of frequency F1 and a note of frequency F2 is, and this should be F sub 1, F sub 2, sorry about that. 2 to the n is F sub 1 over F sub 2, and taking the log base 2 of both sides, we get n is log base 2 of F sub 1 and F sub 2, so this should be log base 2 of F sub 1, F sub 2. Each octave is made up of 12 semitones, or half notes, and the difference in pitch between a key and a piano is a semitone. So if you count the number of keys here between each octave, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 semitones, or half notes, in each octave. And this is just something to know also. A semitone, or the distance between the keys pitch-wise, is 100 cents. So we can divide each of these semitones into a cent, which is a unit of 1/100th of the frequency between them. So let's apply this. Humans hear pitch to around a frequency of 20,000 hertz. How many octaves above A440 is this? So, going back to our equation, we have to find the ratio of the two frequencies. So, one of the frequencies is 20,000 hertz, and the other frequency is 440, because we're talking about above A440. And to find this, all we had to do was take the log base 2 to find the number of octaves of 20,000 over 440. So going to our calculator, we take the logarithm of 20,000 over 440, and to find log base 2, we just divide by log of 2, as we saw a few slides ago. And that gives us 5.506. That's the number of octaves, or about 5.5 octaves above middle C. How many cents would this be? Well, first, how many semitones would this be? So 5.506 octaves, remember there's 12 semitones in an octave, so we can multiply the number of octaves by 12 to get semitones. So let's do that on the calculator. We have 5.506 roughly times the number of semitones in an octave is 12, gives us 66.076 semitones. And how many cents would this be? Remember, there's 100 cents in every semitone. So we can multiply that by 100, get 6,607.6 cents. And maybe we should write our units on these, since this is an application question. 5.506 octaves, 66.076 semitones, or keys on the keyboard, and 6,607.6 cents. In this context, of course, the cents being hundredths of semitones, which is the cent unit we use in music. If a standard piano keyboard has 39 keys after the A above middle C, how many more keys would have to be added to the right to play this note? Well, we need to have 66 from A, so 66 minus 39 is the answer. 66 minus 39. We would have to add 27 more keys to the keyboard. More keys, so let's write keys for this particular answer. Find the frequency of middle C on a piano tuned to the standard pitch with equal temperament. What is the frequency of the C above middle C? Equal temperament just means that's tuned and every semitone is exactly 100 cents, or a twelfth of an octave. So we can then think about, let's go back to my little keyboard drawing. If A4 is 440, we need to find the C below A4, middle C. What's its pitch? There are a couple ways of doing this. We could think about how many semitones up or down. So if we go up, we could find this value and have it. That may be easier because we just have to go up 1, 2, 3 semitones, or 3 half steps, or 3 keys, which is exactly 3/12 of an octave. Okay, so we need to go up 3 keys to get C5, or what is it, C4? I can't remember. We won't write that down. I might have messed that up here. Let me check on that real quick. Yeah, it's C4, and often in scientific pitch notation, these little notations are subscripts, so we'll use that. So C4, this is the C, middle C. The octave above it, C5. So we can find C5 and divide by 2 to get C4. Because remember, C5 is double the number of hertz, or double the frequency. So up 3 keys to get C5. So that would give us 3/12 of an octave up. So 3/12 of an octave would be equal to log base 2, because remember, each octave doubles, so that's why we're using log base 2 of the pitch from C5 down to A4, which is A440, 440 hertz. So we need to solve this logarithmic equation. So 3/12 is 1/4, and we have 1/4 log base 2 C5 over 440. How do we deal with logarithmic equations? Remembering back to the previous slides, we need to do the to the power of both sides, but we don't want to take 10 to the power because that won't undo log base 2. We want to use 2 as our base here. So we take each side as the exponent of 2, and 2 to the log base 2 will undo as long as this is positive, which we know it is in this context. So it just leaves us with 2 to the log base 2 of C5 over 440. And remember, 2 to the log 2 goes away. It's undone. So we get 440 times 2 to the 1/4 is going to be the frequency of C5, which is not our answer. It's going to be double our answer. So we could actually encode all that in here if we wanted to by saying that we're going to find the frequency that's double C4, because C5 is just 2 times C4. Where C4 is middle C and C5 is the octave above middle C. So that would give us 2 times C4. So we can just divide this by 2, or get 220 times 2 1/4. So 440 over 2 is 220. 220 times 2 to the 1/4 gives us 261.625. 261.625 hertz is the frequency of middle C if we're using concert standard pitch, where A is 440 hertz with equal temperament tuning.